Alright, so continuing with that, we're going to look at a few more things related to process scheduling. Scheduling strategies. So all threads may be in a common ready queue, or each processor may have its own queue of threads. Again, this is something which happens when you have multiple processors. You can have one ready queue from which processes are picked and allocated to different CPUs, either by a master server or each CPU picks its own process. That is a separate independent event happening. And the ready queue itself can be one queue, or it can be a separate queue for each processor. So those again are two different possibilities. All of this depends on your system architecture. Now we're going to look at some common challenges which arise when we look at process scheduling. The first and most common of them is memory stalls. So a processor is asked to execute a specific process. So the processor takes the data corresponding to that process from the process control block, and it takes the instructions, it decodes them. The fetch, decode, execute, that cycle which you learned about in computer organization gets initiated. And while executing, if there is the necessity to fetch some data from memory, this is going to take a lot of time. If the data required is there in the cache memory, then it's very quick to retrieve, and you can almost instantaneously proceed with the execution. But if it is a cache miss, if the data you're looking for is not there in the cache, you have to go to the main memory, locate the correct memory address, pick up your required data from there and come back. How that happens is something you have learned in computer organization. So when that happens, that's going to take a lot more time as compared to retrieval from cache. So in such cases, the processor has to sit and wait until the data is picked up and fetched back, right? So it has been observed that the processor may spend up to 50% of time waiting, which is a lot of time being wasted, right? So that's one important problem. How do we solve this problem? Is by assigning multiple threads to every core. So a thread, let me remind you, is one subunit or one sub part of a process. So, and a core is just another term for the CPU. So what do we do here? We assign multiple threads or multiple processes to every CPU. The CPU will start working on one process, and if that process requires some data to be fetched from the memory, while the signal has been sent to retrieve data from the memory, instead of being idle and waiting, this CPU will switch to another of the assigned processes. So this keeps the CPU busy, reduces idle waiting. That is the solution to the memory stall problem. One more important concept, especially in symmetric multiprocessing, is load balancing. So when we looked at symmetric multiprocessing, this slide said one of the major advantages is load balancing, right? Which means the tasks are more or less evenly distributed among all available processors. There is no imbalance of load. So how is this accomplished? We try as much as possible to distribute tasks evenly. So whenever a processor is free, it goes to the ready queue and picks up a process. It does not sit idly and wait for some other process to deal with all the processes which are waiting in the ready queue. Also, we have something called push and pull migration. So what happens is, in push migration, if a processor feels like it has too many tasks to deal with, too many processes to take care of, it will push away one or more tasks. So this is like, if you feel like you've been overburdened with too many tasks, one thing you will try to do, if and when possible, is to delegate some of those tasks to someone else who's capable of doing them, right? So you will keep the most important or most urgent or most interesting, some tasks you will keep to yourself, and whatever can be done by another person, you will try to delegate it. That is exactly what push migration is. So when a processor feels like it has too many things to do, it will push away one or more tasks back into the ready queue. And in pull migration, another process, which is another processor, another CPU which is idle or which does not have too much load, will pull or take up that task. So when you try to delegate a task, obviously you will not delegate it to someone who is just as busy as you. You will try to look for someone who has time to spare, and you will delegate the task to them. If they if they have time and if they are capable and interested, they're going to accept and they're going to take up that task on themselves, right? So that is what pull migration is. So if another processor is relatively idle, then it will pull that task onto itself. So this is how we ensure that no single processor gets overburdened with too many things to do. That is load balancing. One last concept we will look at in relation to multiprocessing, and a very important concept at that is processor affinity. So we know that we have a ready queue. The ready queue has processors. You have a bunch of CPUs. Some entity is picking up a process from the queue and assigning it to a CPU. We also know when a process is assigned to a CPU, that CPU will take up the data corresponding to this process. From the process control block, it will take that data, it will start writing whatever. We also know from our knowledge of computer organization that whenever your CPU uses or accesses some data from the memory, it stores a copy of that in the cache for a while, so that if you want to access it again in a short duration of time subsequently, you don't have to go all the way back to the main memory again. So that is exactly what happens with process execution also. When the CPU picks up data from the PCB and works on it, a copy of that data is also stored in the cache. So if some preemptive scheduling is happening or some interrupt comes or for some reason the CPU is forced to stall the current task and deal with another task, and the CPU deals with it and then it wants to come back to this task, it does not have to pick up the data from the main memory again, it just needs to go to the cache and retrieve it. Whereas if this CPU was executing this task, let's call this task P1, so the CPU was executing P1 and then some interrupt or something happened, P1 was stalled, the CPU went to deal with the interrupt or whatever, and then the scheduler or the dispatcher allocates P1 to another CPU. Then what happens is that CPU cannot access this CPU's cache memory. So that CPU has to go all the way back to the main memory and retrieve the data corresponding to your P1. So what is happening here is there is a trade-off between your load balancing and processor affinity. So if you fix that this process should only be executed by this processor, irrespective of how many interrupts come in between, how many times this process is stalled or suspended temporarily or made to wait, then the wait time obviously becomes long when you keep having more and more interrupts, but the memory retrieval time is almost instantaneous because this processor has all data pertaining to this process stored in the cache. It doesn't have to go back to the memory again. So what happens is load imbalance. This particular processor has to deal with all the interrupts as well as this temporarily suspended P1. Too many tasks. But the memory retrieval time or the wait time becomes very less. On the other hand, if you say, I don't want my process to wait. If this processor is dealing with P1 and some interrupt comes, let this processor deal with the interrupt, I'll take P1 and I'll give it to the next processor. So if you do that, the wait time becomes almost zero, or at least the wait time is reduced significantly. But every time a context switch to a new CPU happens, the data has to be fetched from the main memory again, so that will take time. So in that case you have load balance. This is what you see, right? This one, the first CPU, it was dealing with something and then some interrupt came, so it feels overburdened in one sense, so it's doing a push migration. The second CPU, which is idle, is doing a pull migration and taking up your P1. So there is load balance, but waiting time, memory stall, retrieval time becomes too much. So the point here being, there is a trade-off between your load balance or imbalance and the time taken for memory stalls or retrieving data from memory versus cache. So processor affinity deals with that. Processor affinity as in a sort of attachment kind of thing, right? So when a process has been put into a processor, that processor stores the corresponding data in a cache. So that is what we refer to as affinity. So in that we have two types, soft affinity, hard affinity. So in soft affinity, we try to keep the process on the same CPU. So that's the first case I mentioned. No matter how many interrupts come, I want this CPU only to deal with this process. So what happens In this cases, the memory retrieval time is very less. There are no delays in that respect, but there is a lot of load imbalance. Hard affinity, on the other hand, you have a subset of CPUs. You have like 3-4 CPUs or a bunch of CPUs out of all the processors you have, and you say this processor can run on any of these. So it's not specifically one. It is not all of the cores, so you don't keep jumping around from one core to another everywhere, but you specify a subset, 3 or 4 cores, and you say this process can run on any of these. So to some extent you have a load balancing. At the same time, there are at most 3 to 4 CPUs which your process keeps jumping between. So the cache retrieval time also maximum 4 times, 4 jumps 4 times. The 5th time it is allocated again to one of those 4 CPUs. So in the 5th time it doesn't have to go back to the main memory and retrieve it. So the time is also to some extent reduced. So that is hard affinity, which is how you try to strike a balance between load balance and memory retrieval time.